you to the third instalment of the NZSEE webinar series, an introduction to seismic hazard analysis. Today, Professor Brendan Bradley will be providing us a crash course in what seismic hazard analysis is and highlight some of the science behind the numbers. For those of you living under a rock, Brendan is a Professor of Earthquake Engineering at the University of Canterbury and a Director of Quake Core. Brendan is also a core member of the NSHM revision team. This working group is responsible for deciding the direction of the National Seismic Hazard Model Framework and for assimilating the outputs of the various working groups into the final project deliverable. Just a little bit of housekeeping. For this webinar, the chat bar is disabled for attendees, but if you do have a question, please enter these into the Q&A section and Brendan will get to as many of these as he can at the end. So we're really short on time, so I'll just let Brendan to get into it.
Great, thanks, Tony. If you stop sharing, then I can load up the presentation. Wonderful. Okay, good afternoon, everyone. So as Tony mentioned, the brief, shall we say, that I have today is to give an introduction to seismic hazard analysis. Obviously, the broader context for doing this is associated with the release of the 2022 update of the National Seismic Hazard Model. But in an hour, really, my intention is just to cover off the foundational material to enable people to actually understand some of the technical metrics and associated products that come out of the National Seismic Hazard Model, rather than get into some of the more advanced science that was actually implemented in the model itself. So hopefully by the end of this hour, you'll be in a better position to understand subsequent technical seminars. For example, Matt Gerstenberger will deliver a subsequent presentation explicitly about the National Seismic Hazard Model itself. I'm going to draw on some concepts, figures and examples from this textbook here, published with Jack Baker from Stanford University and Peter Stafford from Imperial College in London. And I'll circle back at the end just to provide some more detail for people that want to learn beyond what's particularly covered in this hour seminar. So just as a sort of outline for content to cover in this presentation, I'll go over the motivation for seismic hazard analysis methods, use a simple example at the start just to provide a bit of intuition and context for some of the subsequent material. Then go into a bit more detail with each of the two main ingredients associated with the seismic hazard calculation, which is seismic source models and ground motion models. And then having covered those two ingredients in a bit more detail, revisit that simple example and expand on it incrementally to look at increasingly more complicated and subsequently more realistic calculations associated with the probabilistic seismic hazard analysis, or PSHA calculation, and then also some typical outputs, including the concept of seismic hazard disaggregation. So as overall motivation, we need to consider ground motion shaking probabilistically, and in particular, we can't get there from direct observation, and so that's the basis for the adoption of this method, probabilistic seismic hazard analysis. We're typically defining the results of such seismic hazard analysis using what's shown here on the left-hand side, a ground motion hazard curve, which you can see on the y-axis has the annual rate of exceedance of a certain level of ground shaking, and on the x-axis has some measure of ground motion intensity, which I'll talk in more detail subsequently. And we're typically interested in relatively low rates of exceedance on this curve. So many of you will be familiar with the use of such information in design codes. For example, in 1170.5 2004, we use 1/500 years and 1/2500 year return periods, which relate to 2 times 10 to the -3 and 4 times 10 to the -4 on this diagram. And because of these relatively low rates of exceedance and the limited amount of time that we've observed ground motions instrumentally, in particular, that even where we have instrumental recordings, we generally don't have them at our particular location of interest, then direct observation of this hazard curve is not practical at these desired rates of exceedance. So instead of having a purely observation-based version of this curve, instead we take an approach where we build this curve based on 2 key building blocks. The first one, how earthquakes happen on nearby seismic sources, and then the resulting ground shaking if one of those potential ruptures does occur. And then probabilistic seismic hazard analysis is the methodology by which we combine these two models numerically. So just by way of example, when we're talking about seismic sources, we might be dealing with a region like this, where we're describing all of the major faults that are located in the vicinity of our source. And then when we talk about ground motions, we might be talking here about some metric like peak ground acceleration and how we understand the behavior of ground motions to vary as a function of things like magnitude and distance. So here we have an example from the 1999 Chi-Chi Taiwan earthquake, where on the left-hand side, we can see the observations of peak ground acceleration spatially, and on the right-hand side, we can see the amplitudes of those peak ground acceleration as they vary with distance from the seismic source to the instrument location. You can see in particular here a comparison drawn between a ground motion model shown in red, and notably you can see that for a given source to site distance, there's a relatively large variation in the observed amplitudes of the ground motion, and really this necessitates us adopting a probabilistic approach where we try and catch that scatter explicitly rather than just ignore it completely. So as I mentioned, to start from the outset to build some intuition for this problem, let's consider a simple hypothetical example where we have a site that's surrounded by two ruptures that you can see here. The first one, rupture 1, has a 1 in 20 chance of occurring annually, or 0.05, and rupture 2 a 1 in 100 chance of occurring annually, or 0.01. And then on the right-hand side, we have a table of a conceptually and extremely simple description of the predicted ground shaking should either of these two ruptures occur. So we're going to assume, just to make this example really simple so I can illustrate the concept rather than get bogged down in the mathematics, that each of these ruptures can produce one of three different levels of ground shaking, either 0.1G, 0.2G, or 0.3G. And in that table, you can see the relative probabilities for each of those ruptures. So we have a case where rupture 1 is 5 times more likely, but you can see from the table that actually if the rupture occurs, rupture 1 generally produces lower levels of shaking, most likely 0.1G, whereas rupture 2 produces slightly higher levels of shaking. So if we wanted to compute the annual probability of a peak ground acceleration of 0.3G due to any rupture at the site, then what we do is we take the likelihood of the rupture occurring. So for example, for rupture 1, that's the 0.05, and we multiply that by, if that rupture occurs, what's the probability that the ground shaking will be 0.3G, which is the value of 0.02. And then we repeat the same process in the case of rupture 2, where we have the probability of the rupture occurring, 0.01, and then the probability that if that rupture occurs, it produces a ground shaking of 0.3G. And so we get that answer 0.003. We can obviously do the same thing if we ask a slightly different question. In this case, rather than the probability equaling a certain value, we ask that it's greater than or equal to 0.2G. And so in this case, the calculation is similar, but now in the bracketed terms, we have two values, which is either the 0.2G or 0.3G that you can see in the red box. And similarly, on the rupture 2 case, the 0.4 and the 0.2 that's indicated in the blue box. And so we have those two values that you can see, 0.003, the probability for 0.3G, and 0.016, the probability for greater than or equal to 0.2G. So we can repeat that calculation also for the value of 0.1G, and then we can plot it on an XY plot looking something like this. So we have on the x-axis peak ground acceleration, on the y-axis the probability of that level of shaking or greater. And you can see here that we're describing the seismic hazard curve in a few different ways. So first, we have the contribution from each individual source, rupture 1 and rupture 2, as well as the summed contribution of those two sources, which is described here as the total hazard. So that basically is the essence of our seismic hazard calculation. And the only thing that changes from this simple example is that the input models for the seismic source and the ground motion become slightly more complicated. More generally, we can describe the calculation that we just worked through using this seismic hazard summation that's shown here. And although obviously it looks a little bit more detailed in terms of mathematics, the concept is still the same. that we have a summation over all possible ruptures. In that previous example, there were only 2 possible ruptures. And then for each rupture, we combine or we multiply 2 different terms. One, the probability of that ground motion occurring, which is given to us by a ground motion model. And 2, the rate at which that earthquake occurs, which is given to us from a seismic source model. And so we'll go now sequentially into each of those 2 in detail. So the first one, seismic source models. We need these because we need models for the sizes and locations of all future possible earthquakes. And so in the next 5 or so slides, we'll go over a brief example of how these models are characterized. And again, just because of available time, I'll skip over much of the details, but hopefully it will give you the key essence associated with these models. So the first, in order to focus on the key attributes of these seismic source models, we need to describe where earthquake sources occur. Of course, we know in general that the majority of earthquakes occur on tectonic plates or at the boundary of tectonic plates more accurately. And we see that in terms of historical seismicity, for example, shown on the right-hand side of this figure. But we also know that earthquakes do occur in between the plates as well as within the plates themselves. And in particular, that we do see extremely wide variation in occurrence rates from extremely active high seismicity regions through to very low seismicity regions. We also, of course, have different types of tectonic settings, and shown on the bottom left-hand here, we can sort of characterize them into 4 main types, depending on whether the plates are diverging from each other, whether they're moving beside each other, or whether they're colliding with each other, either forming subduction zones or collision boundaries that you can see there. In terms of our seismic source model, the most important idea is that we need to account for all possible earthquake sources, despite the fact that we obviously can describe some potential seismic sources in more detail than others. And so the figure on the right-hand side here just gives a sort of schematic illustration of the main different types of seismic sources that we've described. In particular, where we have relatively good definition of potential earthquake sources in terms of their geometry, we describe those using what we refer to as fault sources. Whereas in regions where faults do exist, but we can't characterize them very well, instead of trying to define these sort of linear features with relatively poor definition, instead we make use of what we refer to here as area sources. So it's, as you can see in the schematic on the right-hand side, this broad region has a certain level of seismic activity. And by defining it as a broad region rather than individual faults, the only thing we lose is the precise geographical distribution of where those individual ruptures are. So there's a general trend as we learn more about the seismicity and the geology and the tectonics of a region, we progressively make use of less and less seismic activity on area sources, and we convert more and more of that activity onto well-defined fault sources. For each one of these sources, whether they be a fault source or an area source, we need to describe the relationship between the magnitude of potential earthquakes that they produce, as well as the frequency with which those earthquake magnitudes will occur on the source. And the most basic model for that magnitude frequency description is what's referred to as the Gutenberg-Richter relationship. It's given by that equation that you can see on the bottom left-hand side. And it describes on the left-hand side of the equation the log 10 rate of number of earthquakes exceeding a certain magnitude. And that's a linear function of the magnitude itself. And those 2 parameters, A and B, are empirical coefficients that are calibrated based on observational data. You can see an example for that shown on the right-hand side image. The A value represents the overall activity rate. So for example, how many earthquakes occur with a magnitude above 2.5 in this particular figure that's shown. And the B value represents the relative rate at which larger magnitudes occur compared to small magnitudes. And it's generally common that the B value sits around about 1, which then means that for every 1 magnitude increment increase, so going from magnitude 4 to magnitude 5, we have a factor of 10 less events of magnitude 5 than of magnitude 4. So that's a useful rule of thumb to keep in mind for a B value of 1, which is very common. So the ways that we can constrain these magnitude frequency distributions depend primarily on what part of the magnitude frequency distribution we're focused on in particular. But broadly speaking, we can use three main data sources. We can make use of directly observed earthquakes. So the figure on the left-hand side is showing seismicity in a region determined from instrumental catalogs. So earthquakes occur, they're recorded by networks like GeoNet, for example. And so we know the location and the magnitude and other features of those earthquakes. So we can look at that seismicity catalog over time to understand how likely we get earthquakes of certain magnitudes. But as alluded to in some of the opening remarks, because of our limited duration for which we've had dense seismic networks, we generally can only provide strong constraint on observed earthquake rates for relatively smaller events. That's indicated by the bracketed statement there. And therefore, when we want to start making use of, or start constraining these magnitude frequency distributions for larger events, which obviously govern the seismic hazard in many locations of interest, we need to go beyond just looking at observed seismicity and start drawing on other data. And paleoseismic data, or geologic data more broadly, provides particularly good constraint for those larger events. So one example that you can see shown in this particular figure from the USGS is associated with a tectonic offset of a meandering stream channel. So shown in red here is the current trajectory of the stream, and then you can see that there's a relatively linear offset feature there where presumably prior to that offset, actually that stream used to follow the direction indicated by the orange line there. So we can identify the lateral distance of that particular stream offset, and we can also do carbon dating or some other dating in order to determine the age of the deposits that have been offset. And from that overall lateral displacement and the age of the deposits, we can get an estimate of how much displacement, how often is moving due to that fault offset. The third component that we can use to constrain magnitude frequency distributions is the rate of strain accumulation in the crust from geodetic measurements like GPS, for example. And that's really complementary to these other two data sets. That can either be applied at sort of the overall plate boundary level, so how fast are two tectonic plates moving towards each other or sliding past each other, for example. But increasingly, geodetic methods can also be used to understand deformation within the crust near the plate boundaries as well, which is providing some quite unique insights. So that really provides a very high-level overview of seismic source models. So now I'll turn over to a similarly high-level overview of ground motion models, which is the second important ingredient in the seismic hazard calculation. So given an earthquake rupture, we need to predict the intensity of ground shaking at a location of interest, and we make use of various predictive models that I'll cover relatively briefly here. One of the important things from the outset when we're trying to predict this ground motion is specifically we're actually trying to predict a metric of ground shaking intensity and not the entire time series itself. So on the right hand side here are some examples of ground motion time series. From an engineering perspective, while we can do advanced analysis using response history methods, more often than not, we're dealing with simplified analyses that might be sort of pseudostatic or response spectrum based in nature. And therefore, it's sufficient for us to quantify the complex ground motion time series just using a simple intensity measure here. For example, things like peak ground acceleration or pseudospectral acceleration or significant duration. As sort of was alluded to in the example mentioned before about the 1999 Chi-Chi Taiwan earthquake, we do see a large amount of scatter in the amplitudes of observed ground motions as a function of metrics like magnitude and distance. And this is shown here in the particular figure through the probability distributions that you can see, normal distributions. And so in particular, these ground motion models not only provide us sort of a mean and standard deviation of prediction, but we use that explicitly to understand the probability that the intensity measure, IM, will exceed some value X given a particular rupture at a particular site. So these Predictive models almost always make use of the standard normal cumulative distribution, or CDF, that's annotated here. In this particular schematic example, the level of ground motion shaking that's of interest is 0.4 G for spectral acceleration at 1 second on the y-axis of this figure. And then the ground motion model provides a prediction for the mean and the standard deviation of that particular intensity measure, in this case, spectral acceleration at 1 second. So in the schematic at the bottom, you can see a predictive model shown with a median in the solid black line, and plus or minus 1 standard deviation about that median shown with the dash lines. And then the annotated for 3 different distances of 3 kilometers, 10 kilometers, and 30 kilometers are the predicted distributions of ground motion from a particular model that I'll discuss on the next slide. And then the shaded region of that distribution is the expression on the left-hand side, which is that probability that we exceed that level of ground motion of 0.4 G. So in essence, these ground motion models provide a mean and a standard deviation that we then can plug into this expression to calculate this exceedance probability of a certain level of shaking. By way of example, there's a couple of different models that I'll highlight here for the purposes of illustrating some of the calculations as well as some of the trends. This model from Bohr, Joyner, and Fumao in 1997 is sort of a classic model from the perspective of it was about the point in time where models started to become beyond this, too complicated to write down and sort of almost calculate by hand with pencil and calculator. So you can see here this model, although it has several different sort of descriptions, actually in essence it has 3 different predictive variables. You can see an M for the magnitude of the earthquake, an R for the distance from the earthquake source to the site, and VS30, which is a descriptor of the local site conditions at the site. It has 7 different coefficients, the A0 through A6. And it was developed using a database of 112 ground motions, which at the time was large, but obviously compared to what's available today is relatively small. And then for comparison, the Chow and Young's 2014 model, which is reflective of contemporary models used today, in this case for active shallow crustal earthquakes, has 11 different predictive variables relative to the 3 magnitude, distance, and VS30 mentioned above. 45 different coefficients, and it's calibrated based on about 12,000 ground motions. So a factor of approximately 100 more observed data compared with the model developed in 1997. So from observed ground motion data, as well as comparison with these 2 different models, which I'll shorten to BJF97 and CY14, there's a few key trends that we can pick up with respect to how ground motion amplitudes vary as a function of key features like magnitude and distance in particular. So the figure on the bottom left here shows the variation in spectral acceleration for 1 second oscillator period as a function of magnitude, where the data in blue is observed ground motions globally that are observed at a distance of 10 to 20 kilometers. So let's say 15 kilometers on average. And then in orange is data observed between 80 and 100 kilometers, so about 90 kilometers on average. So as you might expect, we see that as the magnitude increases for all other things the same, for example, distance and site conditions, we see an increase in the observed level of ground motion shaking. The scatter that we talked about previously is obviously seen here in the slides as well, where the y-axis is in log scale. So you can see that from sort of the largest to the smallest value for a given magnitude, there's up to about a factor of 10 differences in the observed ground motions. Some of that scatter is due to the fact that we're just plotting acceleration with magnitude here, and we're not accounting for things like site conditions, for example. But much of that scatter remains even once you introduce the appropriate dependency on things like site conditions as well. Although not shown here, hopefully it would be appreciated conceptually that as the magnitude increases, the duration of the ground motion also increases as well, but simply because a larger magnitude involves a bigger fault, and that larger fault takes longer to rupture as well. And there's also some frequency dependence that's not shown here. That means that the shape of these lines vary a little bit as we change the oscillator period of these plots. but the trend still remains the same, that increase in magnitude leads to a general increase in spectral acceleration. Similarly, the other key variable is how ground motion amplitude changes as a function of source to site distance. So here again, we see observations from the same database now for data in blue between magnitude 3.3 and 5, between 5.3 and 5.7, so 5.5 on average, and then in orange between 7.3 and 7.7, so 7.5 on average. So obviously the trend from the previous slide holds here, that the larger magnitude 7.5 data lies above the data based on magnitude 5.5, and we see the same trend for both of these data sets, that shorter source to site distances lead to larger levels of ground motion shaking. You'll notice that again, despite the scatter, there is that general trend, and if we look at the slope of that line in particular, as we move to shorter and shorter distances, you notice the slope of those lines starts to reduce. So we often refer to this as saturation in the amplitude of the ground motion, and in particular the degree of saturation tends to be larger for larger magnitude earthquakes, and that occurs because as we get close to the fault, it's really the strength of the seismic energy released nearest to the site that makes the difference. And so if you're only located 10 kilometers from a magnitude 8 earthquake, that magnitude earthquake might have an overall length of sort of 300-400 kilometers, but part of that seismic energy released at the very end of the fault might produce actually quite weak ground motion by the time it travels a few hundred kilometers to get to that nearest point of your site. So as the size of the fault becomes really large and you get quite close to the fault, you get this saturation of amplitudes. So those are really the two most important features, and hopefully relatively intuitive, that ground motion intensity increases with increasing magnitude and decreases with increasing source to site distance. The other important factor is associated with site conditions, and that's most commonly quantified using the near surface shear wave velocity, in particular the 30-meter time average value, VS30, but it can also obviously be affected by deeper sedimentary properties or crustal rock properties. It depends on other features of the earthquake source beyond magnitude. So for example, style of faulting, whether it's a normal, reverse or stripe slip fault, whether it's a crustal fault or a subduction interface rupture, for example. It also depends on other features like the rupture geometry, the depth of the rupture, if it's a dipping rupture, whether you're sitting on the footwall or the hanging wall of the fault, and then finally kinematic features like rupture directivity, if the rupture propagates toward the site or propagates away from the site, that influences ground motion intensity as well. But some more subtle treatment of those features is beyond what we can cover today. Okay, so now having covered some of those basics of seismic source models and ground motion models, let's return back to our seismic hazard calculation with that little bit of extra knowledge and incrementally increase some of the complexity of that calculation that we've visited from the outset, just to sort of highlight some of these important trends. So this was the equation that we looked at a little bit before, and now we've covered some of the important elements of the seismic source model and the ground motion model. So on the right hand side, that image of the seismic source model, hopefully now you can see how that term annotated as lambda rup I is the rate lambda of all possible ruptures that can occur. So the index I represents each possible rupture. And then we use this figure over on the left-hand side to describe that ground motion prediction, providing us a probability of exceeding a certain level of shaking, which is this longer term here, P bracket IM greater than IM, etc. And then again, that summation over all possible ruptures. Okay, so let's start again with a one rupture scenario where we have a site with a single fault located 10 kilometers away. We're going to start very simple. So this fault can only produce one magnitude, 6.5. Mentioned it's 10 kilometers away, and it occurs periodically with a rate of 1/100 years, or 0.01 per year. And for completeness, the site has a 30-meter shear wave velocity of 500 meters per second. So if we use that model that we discussed earlier, the Bohr, Joyner and Fumal 97 model, not 7 model, And we plug in these three different values, magnitude, distance, and VS30 values. We end up with a predicted ground motion of log 0.17 or a median of 0.17 G. The standard deviation doesn't depend on the magnitude, distance, or VS30, so that's just a constant value of 0.52. And then from our ground motion model, we can plug in those two different values to calculate that probability. So we insert our desired value, in this case, an example of predicting the probability of shaking of 0.2 G, that's that log of 0.2. Our median is 0.17, and then on the denominator, our standard deviation is 0.52. And if we evaluate that expression, we get just a little bit below 40% probability. And then, so that first expression here, that's the output from our ground motion model. And then for this particular simple example, our seismic source model is defined simply by that geometry shown in the schematic figure on the left-hand side, as well as the rupture rate of 0.001. And so then we can calculate our ground motion rate, which is just the product of those two different terms. So 0.378 times 0.01 gives us 0.00378. So that's our evaluation of the seismic hazard curve for a single value of 0.2 G. So we can repeat that, for example, here for a value of 0.5 G. The thing to notice is when we change the level of ground motion amplitude from 0.2 to 0.5 G, the only thing that changes in these equations is that 0.2 to 0.5. So our median still stays the same and our standard deviation still stays the same. So we get a different value of 0.0191, and then again, we multiply that by the same rate from our seismic source model of 0.01. And so we can repeat that at many different levels of ground shaking, but on this figure here, we're annotating just those two values of 0.2 G and 0.5 G. So we get the seismic hazard curve. Notice that from the simple example that we talked about at the outset, we discretized the ground motion distribution to only be able to produce three different levels of shaking. In that example, it was 0.1 G, 0.2 G, 0.3 G, whereas now we're using a slightly more realistic example where we have a continuous distribution, so we can evaluate any values on the y-axis of the hazard curve, and then we end up with a very smooth curve rather than sort of a discrete curve with just 3 points like we had in that opening example. So we can see here the two different values annotated, as I mentioned. There's also a third point that's relatively easy and quite useful to provide a bit of a sanity check. So for this particular example, we have only one seismic source. It has a rate of 0.01, and therefore we can always look at the far y-axis intercept for an x-axis value approaching 0, because we know that for a ground motion intensity of 0, the probability of exceeding that 0 will be probability of exceeding 0 will be 1, and therefore we should always have an agreement between this 0.01, which is the rate of an earthquake, and this y-axis intercept here, which you can see is 10 to the negative 2 or 0.1. So that's a third point that we can get just from inspection to know that our seismic hazard curve is consistent with the calculations we've done here. Okay, let's expand the example just a little bit by now considering a second rupture. And the first rupture that we considered in the previous example will keep the same. So it's the previous example was magnitude 6.5 with a rate of 0.01 or 1 in 100 years. So we'll have the same fault, but now instead of that fault only producing one rupture, it now can produce two ruptures. And that second rupture is magnitude 7.5. It's again at the same distance because it's on the same fault. And now the rate at which that rupture occurs is 0.002 or 1 in 500 years. So again, we use the BGF 97 model to evaluate the mean and the standard deviation of that prediction. And again, we use that mean and standard deviation to evaluate the probability of exceeding different levels of ground motion intensity. And now when we want to calculate our seismic hazard for that level of 0.2 G, we add up the contributions from all the potential ruptures, which in this case is 2 potential ruptures. And so you can see the partitioning of that summation there. We've got the first part that we just calculated in the previous example, and we've got the contribution from rupture 2 that you can see from the calculations on this page. So for 0.2 G, the 0.94 probability of exceedance multiplied by the rate at which that earthquake occurs, 0.002. that gives us these two different hazard contributions from each of the ruptures, as well as adding them together, the total hazard contribution. So again, we can repeat that process for any different level of ground motion, 0.2 G or 0.5 G or some other level. And so now we can produce the same style of plot before, but now we have the hazard associated with each of the ruptures, as well as the total hazard, which is the summation vertically, so to speak, from a graphical perspective, from each of these two. So again, this is our key output from seismic hazard analysis, our seismic hazard curve. One of the important things to note, which is a general trend when we're dealing with more realistic examples, is we often have this sort of Goldilocks zone type situation where for certain levels of ground motion intensity, some ruptures hit the sweet spot between they occur frequently enough and they produce just high enough levels of ground motion that they tend to dominate the hazard, whereas then when you change the level of ground motion intensity, actually they either don't produce high enough ground motion or they don't occur often enough. And so to illustrate that sort of abstract concept a little bit more concretely, if we look at the lower level of shaking that's annotated here, 0.2 G, you see that rupture 1 produces a larger contribution to the hazard than rupture 2, whereas when we look at the value on the right-hand side, 0.5 G, the reverse is true. And so what's happening here for the value of 0.2 G, that rupture 1, which was the magnitude 6.5 event with a rate of 0.01, that occurs 5 times more often than the rupture 2 event. And so that factor of 5 difference is what makes it produce a higher level of total hazard for the site. Whereas when we move to the level of 0.5 G, that rate of rupture between the two different sources stays the same, but now the ground motion probability changes drastically between the two. And so the reason that sort of reddy orange curve drops off much faster is you're getting to the tail of the distribution of the ground motion from that particular rupture. And so it becomes very unlikely that that rupture will produce higher and higher levels of shaking. Whereas because rupture 2 is a magnitude 7.5 event, it's 1 magnitude unit bigger, and therefore its average ground motion is expected to be quite a lot higher. So as I mentioned, we see the dominant magnitude or the dominant seismic source in general will change as a function of the ground motion level that you're interested in. If we go a little bit more realistic again, so rather than just consider one seismic source, one rupture or 2 ruptures on the same seismic source, now we can extend to consider the idea that a given seismic source can produce any potential magnitude between as low as magnitude 5 all the way up to magnitude 8. So you might think of this as a description for something like the Alpine Fault, for example. The rate at which we have magnitude 5 or greater events is 0.05. And again, you're located about 10 kilometers from the fault. So you might be somewhere like the town of Otira, for example, in relation to the Alpine Fault. And so here's the same set of calculations that we would do to sort of incrementally step through all the possible different ruptures that could occur on this fault. We typically we'll treat these calculations by discretizing them. So we'll go from magnitude 5 to 8, for example, shown here in increments of 0.2 magnitude units. So the value of magnitude 5.1 is the average for an increment between magnitude 5 and 5.2. The value of 5.3 is the average between magnitudes of 5.2 to 5.4. From our Gutenberg-Richter distribution, we'll calculate the rate of rupture for each one of these different magnitudes. And you can see as we go to larger and larger magnitudes, those rate of ruptures keeps going down and down. For each one of those magnitudes, given the source to site distance and the site conditions, we can compute the probability that the ground motion exceeds 0.2 G. And so you'll notice here that for all other things equal, as the magnitude increases, this ground motion probability increases from at the top here, value quite close to 0, all the way down to the bottom to a value that is almost 1. And then by multiplying these two columns together, the rate of rupture and the probability of ground shaking, we get this incremental part of the hazard curve. And then if we sum up over all of these different probabilities, we end up with our final rate of exceeding that level of shaking, which is our seismic hazard curve. Okay, up until this point, we've been talking with some relatively simple examples. So we've had a simple description of the seismic source and a simple ground motion model from 1997. I won't go into the detail because of time of talking about some really advanced models that are contemporary, used for seismic sources and ground motion models that'll be covered in a subsequent seminar by Matt Gerstenberger as to what was actually used for the National Seismic Hazard Model. But suffice it to say that these hazard calculations require many inputs, and these models are imperfect, and actually there are competing models. So we have different models to describe the ground motion prediction. Some of them account for certain phenomena or make certain assumptions that then alternative models make slightly different assumptions. And so from a scientific perspective, we can't outrightly reject different models, and therefore we want to provide a mechanism by which we can account for these alternative but scientifically plausible models. We refer to this as epistemic uncertainty in a seismic hazard analysis jargon, and epistemic here representing limitations in knowledge. And we use a mechanism referred to as logic trees to try and handle the bookkeeping associated with these different possible modeling options. So here's just a simple example of a logic tree extending that Gutenberg-Richter hazard calculation as before. So instead of having a single model to describe the seismic source and the ground motion prediction, we might have the rate of all possible events. In that example before was 0.05, but actually there's some uncertainty in that estimate. So it could be slightly lower than that at 0.03, or it could be slightly higher than that at 0.07. And we will just define different weightings to represent our degree of belief that those different numbers are reflective of the true solution. Similarly, for our Gutenberg-Richter representation of the seismic source, we need to define what is the maximum possible magnitude that can occur. And so again, we might define 3 different values here to represent that or as an approximation to that distribution of what the truth is, and with 3 associated weights that add up to a value of 1. And then finally, with our ground motion model, we can have alternative different ground motion models. We talked about the BJF 97 model and the CY14 model, but there are other models that could be used there as well. And so for each one of these different combination options, we can compute the seismic hazard, and then we can weight that seismic hazard according to the multiple of the weights along each of these branches. So for example, we can adopt a total activity rate here of 0.07, which has a weighting of 0.3. We can then adopt a maximum magnitude of 8, which has a weighting of 0.3, and we can adopt the BJF 97 model with a weighting of 0.3. And that would give us one seismic hazard curve, and we'd do 0.3 times 0.3 times 0.3 in order to get the overall weight that's assigned to that individual branch of the logic tree. So for each one of those particular combinations, in that simple example where we had 3 different modeling options, each with 3 different branches, we get a total of 27 different outputs. And so you can see 27 light blue lines here that are referred to as individual branches coming from the logic tree. Then for each individual x-axis value where we calculate the seismic hazard, we can compute a weighted average or a mean value, which is shown in the solid line, or we can compute any other statistic or percentile that we want. For example, the median or the 50th percentile, as well as the 15th and 85th percentiles that are annotated here as well. So this is the way in which we define or treat epistemic uncertainty. We end up with these logic trees. And so we actually have a distribution on the seismic hazard. So there's some range at which the rate of these different levels of shaking can occur. And really the idea is over time, as we increase our knowledge, we're in a position to potentially reduce some of this epistemic uncertainty. Or conversely, we can look at the sensitivity of these hazard outputs to various different inputs in order to understand which components of the model, either the source model or the ground motion model, produce the biggest variation in the results, or even dig a little bit deeper to understand what particular part of the source model is causing the wide variation, or what particular scenario for the ground motion model is causing that wide variation. Okay, the last thing I want to touch on very briefly is this notion of hazard disaggregation. So the hazard curve represents a combined effect of all potential future earthquakes at the site. And so while that's important because ultimately we design structures at a certain location for any potential future event rather than worrying just about one single potential threat, when we combine all of these different potential earthquakes and just define the output in terms of a seismic hazard curve, we do lose this notion of what is the underlying causal earthquakes that pose the greatest threat to our site. So we want to ask the question, what contribution does an individual rupture represent to that overall hazard? And can we compute features like a mean rupture to develop a bit more of a sort of visceral understanding of the seismic hazard rather than just a simple seismic hazard curve? So that this idea of understanding the hazard in a little bit more detail broadly falls under the topic of hazard disaggregation. So if we refer to that two-source example that we discussed earlier and ask the question, what is the fraction of the total hazard that comes from each of these two different sources? So for the value of 0.2 G spectral acceleration, we have the rate associated with the hazard coming from rupture 1, the rate associated with the hazard from rupture 2, and the overall hazard rate. And so we can simply take the rate coming from each rupture and divide it by the overall hazard in order to work out the fraction of the hazard or the probability that it's that rupture that produces that level of shaking. And so for this particular example, rupture 1 produces about 67% of the overall hazard and rupture 2, 33%. But this idea becomes much more useful as we go to more and more realistic hazard calculations. So returning again to that Gutenberg-Richter example where the source can contribute earthquakes of magnitude anywhere from 5 to 8, we can look here at the same disaggregations in terms of magnitude on the left-hand side for 0.2 G level of shaking and on the right-hand side for 0.5 G level of shaking. And here the height of these histogram bars is telling us the relative contribution of the events of those different magnitudes to that seismic hazard. And so for the 0.2 G level of shaking, you see that the sort of average magnitude is about 6.5, that these small magnitude events, even though they occur very frequently, they don't produce strong enough ground motions on average. And these very large magnitude events, even though they produce very strong ground motion, they just occur far too frequently. Whereas then once we go up to the level of 0.5 G, you see this histogram distribution skew to the right-hand side. And that's because now the level of ground motion has gone up to 0.5 G. So those events that were dominating at magnitude 6.5 are now making less contribution because they're generally producing levels of ground shaking that are below 0.5 G, and therefore they're not contributing as much to the hazard. So again, this is a nice illustration of the idea that the dominant seismic sources vary as a function of the ground motion intensity. So it wouldn't be right to say a certain earthquake fault tends to dominate the hazard full stop. It's for a given level of shaking. And we also see the same trends when we change, for example, the ground motion intensity measure that we use. So the seismic sources that might dominate the hazard for very short period shaking, like PGA or 0.2 second spectral acceleration, might be quite different than the seismic sources that dominate the hazard for 3 seconds spectral acceleration as well. Okay, so in closing for this sort of introductory seminar on probabilistic seismic hazard analysis, the PSHA calculation combines the seismic source and ground motion models and produces a ground motion hazard curve. We account for uncertainty in the modeling or epistemic uncertainty through different alternative models, and we bookkeep that using this concept of logic trees. And we can use seismic hazard disaggregation to identify the relative contributions of individual sources to the total hazard and determine statistics such as the mean magnitude. And in this seminar, we just went through some simple examples to try and illustrate the key mechanics of the seismic hazard calculation, and really just to provide you with that basis so that you know when you see more advanced examples based on contemporary seismic source models and ground motion models, that the underlying mechanics of the seismic hazard calculation remain the same. So I mentioned at the start that the examples here come from this textbook, and this website has more examples as well as code and videos. in particular some primers on various different topics that go beyond what I'm able to cover today. In terms of other things that I do, there is a course at the University of Canterbury that's a master's course on this topic. It's offered both for people enrolled in a master's as well as people just doing a certificate of proficiency if you just want to do a one-off course. But if, as well, obviously there's many other resources available on the web as well. So just encourage you to try and make use of lots of resources that are available as you try and digest new products such as the National Seismic Hazard Model. So thanks very much for your attention.
Thanks, Brendan. Some really great examples of how the hazard analysis translates to actual earthquake phenomena. Rules of thumb, sanity checks, and a bit of a taste of the many inputs and outputs and how limitations and uncertainties involved in the modelling are addressed. We do have a few questions and upvotes, so I'll start with this one here. Hi, Brendan. When considering seismic sources events in the PSHA, are individual events considered independent? That is, one event does not trigger another.
Yeah, good question, Dijan. In general, we make that assumption that events are independent, although increasingly seismic hazard analysis models can do what we call time dependent. So there is this notion both that the activity rate of an earthquake changes as a function of time. So particularly for large dominant faults in a fault system like the Alpine Fault, they tend to be a bit more periodic in nature. We know, loosely speaking, that fault occurs once every 300 years, plus or minus 100 or so years, but there is some periodic nature and it's not just totally random with a sort of Poissonian distribution with a fixed rate. But more specifically, when you're talking about this idea of triggering, there are some models that are starting to account for this idea that one earthquake can act as a precursor to other earthquakes, but they're often important for small to moderate levels of shaking, but not the larger levels of ground motion that are actually governing the design of our engineered structures. So they are increasingly being used, but they don't have a huge impact for some of our design code implementations.
Awesome. We've got a question here from Merrick. The Alpine Fault example is interesting in that 1170.5 limits design shaking based on a deterministic hazard event rather than using PSHA results. Can you discuss what the potential or perceived issues with using PSHA for determining design motions for specified return periods for sites located close to high magnitude, high rate or of rupture sources?
Yeah, thanks, Tony. Thanks, Merrick. So this is really in the broader context of probabilistic seismic hazard analysis, which is the predominant methodology for seismic hazard globally, with really the historical remnants of the prior methodology, which is conventionally referred to as deterministic seismic hazard analysis. Really here, rather than framing it as what are the potential or perceived issues with PSHA, it's better to flip it around and say, if you use a deterministic approach, 84th percentile, for example, what are the obvious limitations in using that? And so essentially what you're saying is you're designing considering only that particular scenario to occur, and you're assuming it does occur in the lifetime of the structure, and you're ignoring all other potential seismic sources. And then even though you're seemingly being conservative by considering that event does occur, by taking a fixed percentile of the ground motion, in this case, you mentioned the 84th percentile, which is commonly adopted, you're explicitly allowing a 16% chance that if that event does occur, the ground motion will exceed the value that you've designed for. So generally, because of those limitations, that procedure is, increasingly being used less. Seismic design codes obviously have a sort of longer adoption period than the latest science and site-specific seismic hazard analysis in particular. So there are still a few remnants of some of those approaches. But there are some case examples of codes around the world that used to make such deterministic caps that have subsequently started to get rid of them. So I think we're moving toward a point where we completely avoid these deterministic notions and we go straight for a probabilistic basis for our seismic design.
Cool. This question is a little bit outside of the direct modeling, but how is peak ground acceleration measured? Distance, is it assumed it's based on people who've reported the motion?
Yeah, so based on how the question's worded, peak ground acceleration is measured on seismic instruments. There are various different types. We make sure that obviously they're all of sufficient quality to record that type of metric, which is a high frequency measure of ground motion. Distance is measured based on identifying the location of the earthquake using earthquake networks such as GeoNet, and then literally taking the three-dimensional distance from the seismic source to the location of the instrument.
We've got a question on basin edge effects and how does this sit and how do we account for it? Wellington is a good example.
Yeah, so generally here I mentioned sort of two main features associated, like provided some more elaborate details on two main features associated with ground motion prediction. It's dependence on magnitude, its dependence on distance. And then I mentioned several other effects. One of those which I mentioned was sedimentary basins. And so the so-called basin edge effect is a subset of phenomena that we see in sedimentary basins. We can obviously treat that in a simplified manner where we try and collate global data from observation sites that sit near basin edges and develop models for that. Or we can try and do it more explicitly for the individual location or region that we care about. The former is useful because we can collate lots of data, but then it's generic in the sense that each sedimentary basin and hence basin edge is relatively different. And therefore, while the phenomena are understood well on a conceptual level, the actual sort of specifics at a nuance level are a little bit more detailed. So those are really things that, particularly the example of what are we doing in Wellington, are probably a little bit beyond this talk, but simply to say that it is a recognized phenomena and there is effort being devoted to account for it more precisely in seismic hazard models.
We've got probably a couple of minutes for a couple more questions. What is your opinion on the use of VS30 as an input used to capture the effects seen at an individual site? Is there a better metric?
Yeah, good question. So it's not an uncommon question. It comes up a lot. I guess the important thing to emphasize is when we're trying to predict ground motions, we're trying to try and use metrics that strike a good balance between accuracy and generalizability. So if you use an incredibly detailed model of the individual soil profile, then potentially you can do a better job than using a simplified metric like VS30, which really describes the bulk property of the near surface in terms of side effects. But if you do a much more detailed job, then you can only use that model where you have a really precisely defined velocity profile, right? So when we're trying to define seismic hazard at a national level, metrics like VS30 do the best job of giving us some insight into how materials of different velocity cause ground shaking to vary at the surface, while also being a metric that's relatively easy to quantify. Of course, people always have the option of doing site-specific response analysis where you do model the individual stratigraphy of the soil column and then you try and develop a more accurate assessment.
Leading on from the basin edge effects question, there's I guess a statement slash question from Braba in regards to topographic effects, slopes and ridges, and being important for hilly New Zealand.
Yeah, again, common question that comes up. We have done quite a lot of investigation of this in terms of recorded ground motions. The overwhelming majority of seismic instruments in New Zealand are not located on sites where topographic effects are important. That partly reflects the fact that many urban locations in New Zealand aren't on extremely hilly terrain, but also the increasing recognition that there is always topography. It's a question of, is it topography of the ground surface or is there topography in the subsurface, i.e. soil strata are not perfectly horizontal layered. And so the short answer is clearly there are extreme topographic cases where you're on a cliff edge or you're on a extremely steep terrain and highly mountainous regions, but actually more broadly speaking, it's not a major problem in general for urban locations with those
Right.
caveats that I mentioned.
Right, probably time for one more question, a deep one. Can you comment on the difference between the aggregation mean magnitude and the distance compared to the mode?
Yeah, well, I mean, I guess purely from a factual perspective, the mean is the weighted average of that combination. The mode is the most likely. But where probably the question is coming from is more why to use one and not the other in certain situations. The important thing there is to try and understand, if you use a single metric, what is the aim of using that metric? So for example, in terms of things like magnitude, it's often used for magnitude scaling equations for liquefaction. And you can show theoretically that by just using a single value instead of actually summing over the entire magnitude disaggregation distribution, it's the mean magnitude that gives you the best estimate of that overall one. And so the mode tells you the most likely scenario, but because so many seismic sources contribute to the hazard, even the mode rupture can sometimes only have 10% contribution. And so it's not really often the best metric to use.
Right, just ticked over 2 o'clock, so it looks like we're out of time. I'd like to give a final thanks to Brendan for his presentation today, and I'd also like to take the opportunity to invite everyone to our next webinar in our series. In ways, it's a companion presentation which will take place at the same time next week, 1 to 2 p.m. This will be presented by Matt Gerstenberger of GNS, who will delve into the particular technical aspects and the science behind the NSHM update. Expect to see an invite for this presentation later today. So yeah, thank you for everyone tuning in.